In Lab 2, I observed the motion of a stuffed animal that falls straight down when dropped from rest. Similar to Lab 1, I also used Newton's second law, except this time using weight and drag to predict and describe the motion of an object under a changing velocity. And overall, with this experiment, I was able to find 3 representations of this stuffed animal's motion through experimental data and the model data with the effects of only gravity and a model data of gravity and drag. Using Tracker, I calibrated the system to my height and inputted the stuffed animal's mass as 0.02 kilograms. I also set the coordinate axes so that the stuffed animal was moving in the negative y direction. Then I found the point mass at each instance in the object's motion. Overall, I was able to find that the object had a parabolic position versus time graph due to its changing velocity over time. In addition, I was able to extract this information to plug into Newton's second law. We are using Newton's second law to construct the computational model of the stuffed animal's motion with the changing velocity and therefore non-zero net force. See in the code, I plugged in the stuffed animal's mass, its initial position, velocity, and time. Also, because there is a non-zero net force, we have to factor in first the gravitational force W equals negative mg hat, where m is the mass of the stuffed animal, g equals negative 9.8, and j hat is the unit vector. We set the while loop so that it ends at the stop time 0.533 seconds and plug the weight force in for the net force in Newton's second law. In comparing the graph of just gravity with the experimental data, we can see the model overpredicts the falling distance. So we just to improve our model by using Newton's second law and adding weight with drag. So when factoring in the drag force, I found the proportionality constant to be 0.00085, which I then used to plug into the equation F drag equals BV squared to find the drag force. When combining this force with weight force to get the net force, and then plugging into Newton's second law, we also get a very similar graph, but this time with the same ending position. I believe the reason for why the graphs for this model data of gravity and drag were so similar is because the system did not have a lot of drag, as you can see from our proportionality constant. Also, there could have been some experimental errors, such as video distortion while filming the experiment, which could account for some inconsistencies in the graphs. When comparing the time versus velocity graphs of the models with drag and without, we can see that the model with drag has terminal velocity, as it has a horizontal line near the end of its curve, which indicates that the drag force is exactly equal or balanced, so therefore it has a constant velocity on the stuffed animal. If the object was initially thrown downward, the terminal velocity would not occur in the same place, as the starting speed is probably faster than the terminal velocity. This would cause the drag net force to be positive due to the greater amount of drag force applied on the object than if dropped from rest, which would cause the object to then slow down before it could balance out the weight and drag forces to achieve constant terminal velocity.